the example that we left yesterday. Is it okay now? So let's begin with the example that we left yesterday. And it is kind of an example that if I have a space whose measure is infinite, then a sequence that converges almost everywhere, it's not necessary that the same sequence should converge in measure. Okay? We said that let's take R and let's take the back measure. Okay? We know that the back measure of x equal to R is infinite. You can see that Fn, which is the indicator function of n plus 1. We are missing a very basic thing actually. Anyway, so Fn is this. Now what is my claim? My claim is that Fn converges to F almost everywhere, but Fn, does not converges to F in measure. Now, both of things are easy to verify. So we were stuck yesterday because we were not approaching it correctly. So, what we need to do? In order to show this, you have to show that for every x in R, Fn of x converges to f of x as n goes to infinity. And those x for which this is not true has a measure of it. Okay, this is what that we would like to show. Now, there is something even more stronger basically true than what we require actually. So here's the thing. So if I pick and fix an x from R, okay, then I can say that I can always find an m, natural number, such that x is in this interval m to m plus 1. Okay, this is the case. Now I'm saying that, okay, let's evaluate this limit n tends to infinity Fn at this point. Okay. Now, what will be this Fn of x and its limit n goes to infinity? Now, you have to think about it. That I know Fn of x is 1 if x is, so it's like at this particular x, if x is in the interval m to m plus 1. And it's 0 otherwise. Okay? Now, if n is getting bigger and bigger, obviously, so in other words, it's obviously Fn of x must be 0 actually. Are you getting the point? It's not necessary that even if the x is staying in the interval m to m plus 1, but since this n is growing bigger and bigger, obviously, you're going to get Fn of x equal to 0. You distribute it. Okay, here's the thing. Now, what is Fn of x? So, this n is abstract. N is abstract, while x is fixed. So, keeping in view the definition, I would say that Fn of x is 1 if x is in this interval m to m plus 1. Okay? Or you can say that Fm of x is 1 actually. Fm of x is 1 if x is there and it's 0 otherwise. Now I'm saying that when I'm taking limit n goes to infinity of Fn of x, my n is not fixed. It's going to cross this n. So if this n is getting bigger and bigger, okay, you know, it's going to cross this n no matter what m you have actually. Are you getting the point? And hence, what you're gonna get, you will fall in this second situation actually. And you get what do you call 0. Are you getting the point? So this converges basically, okay, so this converges to 0 in general actually, not even almost everywhere. So this converges in general, okay, and if you have this convergence, okay, then what are the points on which the fn of x is not converging to 0? So you're going to say that's empty set. An empty set has measure 0. Okay? So what is a set on which the fn is not converging to 0? So there is no such point. So you're going to get an empty set here. So the measure of the empty set is 0. Hence you can say, so this is precisely what you wanted actually, hence you can say that fn converges to f almost everywhere. Okay. Why fn is not going to converge to f in measure? Okay, what is the definition of, you know, fn converging to f in measure? We have to show that for every epsilon positive, okay, the limit of n goes to infinity, measure of the points, okay, where the fn minus f of x is bigger than epsilon is 0. Okay? Now, is equal to 0. Now, what is this set actually? Think about it. So, x such that fn of x minus f of x is bigger than epsilon. So, if I want to compute this set. So, if epsilon is a positive number and you want difference to be bigger than, sorry, this must be 0 actually. You should say 0. Why? Because f of x, what we are assuming is 0.
So that's greater than epsilon.
Greater than epsilon, obviously, yes. Greater than epsilon. So what kind of set you are talking about? Basically, you are talking about this interval. Because this is a set where the function, you know, can potentially has a value which is, you know, could be bigger than epsilon. Otherwise, if fn is 0, so it's like you can't have this. So R, it's a subset here. Okay. It could be equal to it, or it could be the subset as well. Okay. And in fact, safely we can say this is equal. So if you compute the measure of it, okay, you can say, here's the thing. I want to have this for all n. Measure of an is less than or equal to.
So the limit is this.
Yes. So what I want to see is that is this true for. This must be the interval. So if you compute the mu of this, you're going to get the mu of this actually. And it's going to be 1. And if you take the limit,
It's not going to be.
it's not going to be 0. Okay? So you're going to say that this is an example where f converges to x, but the measure of f is not 0. What is the next thing that I would like to do? There are 2 quick things that I would like to prove, and then we'll move on. So the next I would like to prove So there shouldn't be a theorem actually, which is true in general, which is true for general measure spaces. It says that if I have a sequence that converges to F almost uniformly, then Fn converges to F almost everywhere. Almost everywhere. So what essentially you are saying, so everything. So what essentially, what is the meaning of it? So recall what is the meaning of Fn converging to F almost uniformly? It means that for every epsilon positive, I can find and maybe say E epsilon, okay, set depending on epsilon, such that its measure is less than epsilon, and Fn converges to F uniformly on E epsilon complement. This is what it means. Okay? Now here's the thing. Think about it. So if Fn is converging to F uniformly,
Infinity.
sorry, yes. So here's the thing. If Fn is converging to F uniformly, then on this set, Fn is going to converge pointwise as well. So you get almost everywhere convergence actually. So the only thing that you have to do, you have to think that since you have many epsilons and many epsilon, sets, okay. So mu of epsilon. So what would be the mu of epsilon? So what would be the E epsilon? E epsilon would be the set where Fn is not converging to F. Okay. So what you can do is that you can take all such sets and combine them. Okay. So for every epsilon you have such a set. You take all such sets and combine them, and remove it from X actually, the total space. So you're going to only remain
those we are converging
with you'll only remain with that part where the Fn is converging F uniformly, and hence you could converge this almost everywhere. So this is what the key trick is. So how are you going to prove it? Here's a good proof. I'll try to be precise today as much as possible. Now, for a given natural number, choose epsilon to be 1 over k. Okay? Then, obviously, I can find ek such that I can say that Fn converges to F uniformly on Ek say and measure of Ek complement is less than or equal to 1 over. It's finite if you can replace E and E complement. Should be okay. Alright? And now I want to do, so I can do this for all k's actually. I can do this for all k's. So I'm saying that consider the intersection of all such EKs. In other words, what I'm saying is do the same for all k's actually. Okay. This is what that I'm saying. What would be the interpretation of it? How can I read intersection? That if for k I'm having such an Ek where this is true, then I'm saying that okay, let's do this for all k's. Okay? Not for some case, but for all cases. Yes. But interestingly, this would be, and this is, okay, a subset if you pick a one particular en out of it.
Exactly.
So if I have an intersection here, so it must be less than or equal to one particular n. You getting the point? Ah, no. So, okay. How about if I take complements, this would be still true.
संयुक्त होती है
Huh? No, these are sets actually. So I'm saying that for each such k, you're going to have
सही
an ek complement for which this is true. And I'm saying that do this for all these such k's.
और वो भी इनमें से एक है ना
Yes, so this is one of them.
होल कंप्लीमेंट आई थी
What do you mean by that?
Whole complement.
नहीं, ये सिर्फ इस पर है, e पर है. E पर. So this must be true. ठीक है? I got that? Now if this is the case, then what would be the measure of this k in natural numbers of ek complement? It must be less than or equal to
मेजर ऑफ
mu of
ये
ec or complement of en, and this is less than or equal to 1 over n.
सही है
So in other words, I can make this guy smaller as much as I want it. Okay, so in other words, take n, so take n bigger and bigger and bigger, and this guy will get smaller and smaller and smaller. And hence, eventually I would say
n goes to 30 is good
the mu of this, k equal to 1 to infinity of e k complement is 0. Okay, this is important. Now, take e. So I need a set e actually, which can work in this way for me. In other words, my claim is this or its complement is the set you want actually.
Sir, यहाँ पे zero limit apply करने के बाद आए या limit?
So you can apply a limit, but I can argue generally as well. I can say that if I wish, I can make it smaller than any epsilon. So if something is smaller than any epsilon you want, then it's 0. Yeah. I can make it smaller than any epsilon. Sorry. Alright. Now, so in other words, so I wanted a set that has a measure smaller than epsilon to my chosen number. Okay. So I got such a set actually, which is this. So I need to show what next is that on the complement of this set, the Fn converges to F uniform. That's what I'm writing. Now consider the set E, which is okay. I can use one notation, but it's fine. Complement of the complement, which is going to be the union of k equal to infinity what is called ek. Okay? My claim is that Fn converges to F on each point of this basically. On each point of it. Because keep in view that we wanted to show that Fn converges to F almost everywhere. And I can show it by showing that on this set Fn is uniformly convergent. Or I can show it directly that okay, pick an arbitrary point from here and show that Fn converges to F, pointwise. So in both ways I can do it. Okay, so here's a claim.
सर वहाँ पर नहीं करेंगे। अगर वो वहाँ पर हमने लिखा लिखा हुआ है FN converges to F uniformly और EK अगर एक EK पे कन्वर्ज कर रही हो तो उसको हम नहीं ले सकते कि यूनियन पे भी कन्वर्ज करेगी डायरेक्टली.
You have to give a precise argument that why it should be true. You have to justify it. Okay? So I want to show it precisely. So we claim in white Fn converges to F pointwise on E. Okay? Pointwise on E. And if it converges pointwise on E, that's what you wanted actually. That's precisely what you wanted. So how can I show it? So let's pick a point T in E. Okay? So if you pick a point T in E, what does it mean? There exists an M such that T belongs to this EM actually. Agree? If T is in E and E is the union of such kind of sets, then there must be one set in which at least one set in which this belongs. Now if T is in M and T is in EM, what does it mean by definition actually? So it means that, okay, now as Fn we know, Fn converges to F uniformly on, okay, EM. So in particular is going to converge at, you know,
Point.
okay. Now as okay on EM, so in particular Fn of T converges to F of T as n goes to infinity for all T in E. Okay? For all T in E. T belongs to EM. Okay? And hence I can say that in this manner, no matter what T I should take, I can prove the pointwise convergence actually. And hence I can say that Fn of T converges to F of T as n goes to infinity, or maybe Fn of x converges to F of x for all x in E. That's what you wanted. Okay? That's what you wanted. And what would be the measure of E complement?
जीरो होनी चाहिए.
वो है ना zero. Because this is equal to measure of k equal to 1 to infinity ek complement, which we have already shown that it is.
सही.
So this really satisfies the definition.
It does not converge.
So what does it show? That Fn converges to F almost uniformly, and there is no restriction on the space actually. This is true in general, whether it's finite space or it should be true. Okay. So on demand of Zeller, I'm doing the proof of Igorov theorem again. Okay, because I felt that many people are not happy with it, so let's do it precisely once more. I'll try to do it precisely. Because in Bas, it's not precise, it just jumps actually. So it's just so Igorov theorem says that if the measure of a space is finite, then the converse is true. In other words, Fn converges to F in measure implies
approximately everywhere.
huh?
Approximately everywhere.
So
Everywhere converse.
almost everywhere implies
Uniform.
uniform. Okay? This is what. So here's the proof.
Good.
So what I want to show, so I have to choose an epsilon. For a given epsilon, I have to find a set E, okay, on which this converges uniformly, and its complement has a measure less than or equal to that epsilon. Okay?
So
Here's the thing. So imagine an epsilon is given to me. Okay? Epsilon is given to me. Now since I have this, so that since Fn converges to F pointwise, okay? And there is a set on which this is not happening, but it has a measure 0. But in general, Fn is converging to F pointwise. In other words, so I can say that I can find an n depending on epsilon, okay? N depending on epsilon, and small n depending on epsilon, such that if the index L goes beyond this epsilon, and then the distance between L of x and f of x is less than epsilon. Okay? And the measure of the set such that L of x minus
exceeds
f of x exceeds epsilon
0.
is 0. So this is what
By definition.
is the definition of
Assumption.
okay?
Yeah, assumption.
Now let's listen to the next argument very carefully. So this is true in general actually. So this is true by definition. I just reformulated what is written here.
Assumption.
Okay? So here is the case. Now for each k, take epsilon to be 1 over k. Okay? And for each such epsilon, I can find an n, depending on epsilon. Okay? Alright? I can find an n, depending on epsilon, such that for each k, here's the thing. What do you mean by for each k? So it's like k can be anything from 1 to infinity. I can find one n, so there exists an n, so it's like a union. Okay? So it could be anything from 1 to infinity, such that after this n, for all L after this n, what is happening? This is happening. Sorry, this is happening. Okay? So here's the thing. X such that f L of x minus f of x is less than or equal to 1 over k. Okay? So what does this set is telling us? This set is telling us, so it's like putting the same statement but in a precise form. Okay? Relevant to. So in other words, for each k and this epsilon, I can find an n epsilon, so I can put an epsilon here. Okay. I can also say that, okay, this, if this depends on epsilon depends on this, it's finite. So in other words, for each k, I can find an epsilon. So I'm writing it in union actually. So in other words, there is some n. Okay, could be one, could be more than, could be one.